This is the fourth and last module of chapter 7. This chapter is divided to two parts. In first part we consider Monte-Carlo integration. This is another integration method. This method is based on random numbers and this is a statistical based method. And in second part is devoted to double integration. In this part we introduce two methods, that means trapezoidal method and Simpson 1/3 method to find the double integration of an integrable function. The Monte-Carlo method is a very interesting method to solve different type of problems based on random numbers. The basic principle of this method to find the integration is stated below. A set of random numbers is generated. The Monte-Carlo method is then performed for these random numbers for one random trial. The trial is repeated for several number of times and all these trials are independent. The final result is the average of all results obtained in different trials. So, this principle may be used to find an integration or to solve any other kind of problem. This method is not suitable for hand calculation because it depends on a large number of random numbers. Let the definite integral be I equal to integration a to b gx dx, where gx is the given integrand and it is a real valued function defined on the closed interval a b. Now, this definite integral is converted to a particular form that can be solved by Monte-Carlo method or based on random numbers. So, for this purpose a uniform probability density function, in short it is denoted by PDF, fx is defined on the closed interval fx in the following form: fx equal to 1 by b minus a, where x lies between a and b and 0 otherwise. So, this PDF or the probability density function is also known as rectangular probability density function or uniform probability density function. Note that 1 equal to b minus a into fx when x lies between a and b. So, using this concept the given integration becomes I equal to b minus a integration a to b gx into fx dx. Note that fx is nothing but 1 into b minus a. Note that the integral on the right hand side of equation 2 is nothing but the expectation of the function gx under uniform probability density function. Expectation means the mean value of the function. Thus, the integral I can also be written as I equal to b minus a into integration a to b gx fx dx equal to b minus a into g bar. G bar represents the expectation or mean value of gx over the interval a b for the rectangular probability density function fx. Now, we consider a sample x1, x2 dot 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 is drawn from the probability density function fx. For each such x, the value of gix is evaluated. To get a better approximate value, a large sample, that means the large size of sample, say n, capital N is considered to get better result. Let capital G be the average of all such values of gxi, where I equal to 1 to n, that means gxi is calculated for each sample values and then we calculate the average of such gxi and this is denoted by capital G. That means the equation 4 is obtained as capital G equal to 1 by n summation I equal to 1 to capital N g of xi. It can easily be proved that the g bar equal to g small bar, where the bar represents the expected value of the corresponding coefficient or corresponding quantity. That means we can prove that the expected value of g, which is equal to the expected value of small g. Using this result we can write the capital I, the given integration is approximately equal to b minus a into g bar, the expected value of capital G, which is equal to b minus a into 1 by n summation I equal to 1 to n g of xi. So, this expression equation 5 gives the integration of integration a to b gx dx. In C programming language, if function rand is available in the header file stdlib.h, which generates a random number between 0 and rand max, where rand max is a C constant and gives the maximum integer provided by the computer. Then the C statement float, this is the cost operator, rand by rand max may be used to generate the random numbers between 0 and 1. When the random number is divided by the maximum random number rand max, then the random numbers is converted to 0 to 1. And to get the random number between A and B, the following C statement may be used, which is nothing but B minus A into float of rand, the function rand by rand max. So, this expression gives a random number between A and B. Now, we consider one example. A C program is designed, which is available in the text, to find the integration of the following problem. The problem is integration 0 to 1, 1 by 1 plus x square dx. The result obtained for different values of n are tabulated below. The exact solution of this integral is 0.785398, and for n equal to 500, the program gives the value of the integral, which is equal to 0.790020, which is far away from the exact value. When n equal to 1000, then the value is 0.789626, which is close to the exact value than the previous one. When n equal to 1500, then the value is 0.786979, and it is more closer to the exact value than the previous two values. And when n equal to 4000, then the value is 0.784793. This is the closest value among the values mentioned in the table. So, this sample size, that means n equal to 4000, gives the best answer among the all other tabulated values. It may be noted that when n equal to 10,000, then the value is 0.784094. This is worse than the value obtained for n equal to 4000. And when n equal to 15,000, the value is 0.782420. This is far away from the exact value. So, we can conclude that the large value of n does not give better result for all type of problems or for all cases. The Monte-Carlo method is described to find the integration of an integrable function, and we have seen from the last table that the method does not give the better answer in one execution. To get the better result or good result, we have to repeat the method for several times. So, this method is one kind of simulation based method, and applying the several trial, we can choose the best result from the different results obtained in different trials. Now, we consider the double integration. Two methods, one is known as trapezoidal method and other is known as Simpson 1/3 method, are to be described to find the double integration of an integrable function. Double integration is a particular type of multiple integration, and we know that the double integration is applied in many problems. It can be used to find the area of a particular region, it can be applied to find the volume of a particular surface and many other problems. Let us consider the simple case of double integration. I equal to integration c to d, integration a to b, f of xy dx dy, where a to b is the interval for the variable x and c to d is the interval for the variable y. The integral can be evaluated numerically in two successive steps. In first step, the integration is calculated with respect to x, with respect to the variable x, and taken y is a constant quantity. And in second step, that one is evaluated with respect to y. In second step, the variable is y and x is already evaluated. That is why in second step, the integration is performed over the variable y. Now, we consider the trapezoidal method, which is similar to the method described in module 2 of this chapter. The integral is this one. Assume that y is constant, then we integrate I with respect to x by trapezoidal method, and which is given by equation 7. Note that I equal to b minus a integration c to d f of ay plus f of by dy. That means if we integrate f of x y with respect to x, then we obtain two terms, one is f of ay and other term is b of y, f of b comma y. So the integral is reduces to equation 7, and 7 represents two integral, and the variable of this integral is y, only y is the variable. Now again we apply the trapezoidal method to the right hand side, and there are two integrals with variable y. Again applying the trapezoidal method on these two integrals of the right hand side of the previous equation, we get I equal to b minus a by 2, and this is the value of the first integral obtained by trapezoidal method. This is nothing but d minus c by 2 into f of ac plus f of ad, and second integral gives this expression. This is also obtained by trapezoidal method, and after simplification I is reduces to equation 8, that means b minus a into d minus c by 4 f of a comma c plus f of a comma d plus f of b comma c plus f of b comma d. In terms of x and y, this integration can be written as this form: I equal to hk by 4 into f of x0 y0 plus f of x0 y1 plus f of x1 y0 plus f of x1 y1, where h is nothing but b minus a, that means length of the interval on x, k equal to d minus c, this is the length of interval on y, x0 is taken as 1, taken as a, x1 is b, y0 equal to c, y1 equal to d. In this case, the interval AB is divided into n equal subinterval, each of length h. That means to get the composite trapezoidal formula, the interval for x is divided into n equal subinterval, and interval of y, that means the interval CD, is also divided into m equal subinterval, each of length k. That is x0 equal to a, xi equal to x0 plus ih, xn equal to b, and h is given by b minus a by n. Similarly, y0 equal to c, the starting limit, yj equal to y0 plus jk, k is the length of the interval, ym equal to d, and k equal to d minus c by m. Now integrating equation 6 with respect to x between a and b using the trapezoidal formula as in case of single variable, and we get this expression, that means integration a to b f of xy dx, which is equal to h by 2 into f of x0 comma y plus 2 into f of x1 y plus f of x2 comma y plus dot 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 plus f of xn minus 1 comma y, second bracket close, plus f of xn comma y. So this is nothing but the composite trapezoidal formula for n intervals. Now again we integrate this equation 10 with respect to y, and we obtain this equation. So entire expression gives the composite trapezoidal formula for double integration. After simplification or using the simple notation f of ij equal to f of xi comma yj, the entire expression is written as in equation 11. For simplicity, we can represent the entire formula equation 11 as a tabular form. For x equal to x0, the expression f00 plus 2 into f01 plus f02 plus dot 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 plus f of 0 m comma 1 plus f0 comma m whole into k by 2 is denoted by I0. Similarly, for x equal to x1, the entire expression is denoted by I1, and when x equal to xn, the entire expression is written as In. So using this notation, the trapezoidal formula for double integration can be written as I equal to h by 2 into I0 plus 2 into I1 to In minus 1 plus In. See that this formula is exactly similar to the trapezoidal formula which is applied in single variable case. where ij equal to k by 2 into f of j0 plus 2 into f of j1 plus dot 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 plus f of j m minus 1 plus fj comma m, and this is true for all j equal to 0 to n. So, this expression is nothing but the trapezoidal rule, composite trapezoidal rule, to find the integration with respect to y. So, these two formula, equation 12 and equation 13, is the composite trapezoidal formula to evaluate double integration. Now, we consider Simpson one-third method to find the double integration. In Simpson one-third formula, both the intervals are divided into two subintervals, that is x0 equal to a, x1 equal to x0 plus h and x2 equal to b, with the 3 points on the interval ab. Similarly, the interval CD is also divided into two intervals. The points are y0 equal to c, y1 equal to 0, y0 plus k and y2 equal to d, where h equal to b minus a by 2 and k equal to d minus c by 2. By Simpson one-third formula used in single variable case, taking y is a constant quantity, we get integration a to b f of xy dx equal to h by 3 f of x0 comma y plus 4 into f of x1 comma y plus f of x2 comma y. This is the Simpson one-third formula for one interval or two intervals. Now, applying the same formula on each term of the above equation, we get the following equation, equation number 16. Note that I equal to h into k by 19 into f00 plus f02 plus f20 plus f22 plus 4 into f01 plus f10 plus f12 plus f21 plus 16 into f11. So, this is the Simpson one-third formula to calculate the double integration, and the number of sub-intervals are taken as 2 for x and 2 for y. To get the composite Simpson one-third formula, we prepared the following table of values. For x equal to x0, the expression f00 plus 4 into f01 plus 2 into f02 plus 4 into f03 plus 2 into f02, f04 plus dot 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 4 into f0 m minus 1 plus f0m whole into k by 3 is denoted by I0, and for x equal to x1 the entire expression is denoted by I1, and lastly when x equal to xn then the expression is denoted by In. So, using this notation we can write the composite Simpson one-third formula as I equal to h by 3 into I0 plus 4 into I1 plus I3 plus dot 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 plus In minus 1. That means all the odd suffix of I are multiplied by 4 plus 2 into I2 plus I4 plus dot 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 plus In minus 2. That means the sum of all i's with even suffixes are multiplied by 2 plus In. This formula is nothing but the composite Simpson one-third formula for single variable case, where each I, j are obtained by this expression. Note that the equation 18 is nothing but the composite Simpson one-third formula to find the integration with respect to y. Thus, equations 17 and 18 simultaneously gives the composite Simpson one-third formula to find the double integration. Now, we consider one example to illustrate the trapezoidal and Simpson one-third formula taken h equal to k equal to 0.25. Since h equal to k equal to 0.25, therefore, the values of x are 0, 0.25, 0.50, 0.75 and 1, and similarly the values of y are 0, 0.25, 0.50, 0.75 and 1. Here the function is f of xy equal to 1 by 1 plus x square into 1 plus y square, and for this function and for the values of x and y we obtain the following table of values, and these values are used to find the integration using trapezoidal and Simpson one-third formula. let x be fixed and y be the variable, then by trapezoidal formula on row of the above table we get I0 equal to integration 0 to 1 f of 0 comma y dy. In this case x is taken as 0 and y is the variable quantity, and using this formula we obtain the value of I0 equal to 0.78279. Similarly, I1 equal to this value, I2 equal to this one, I3 is this, I4 equal to 0.39140. So, using this value, that means using trapezoidal formula, we get the value of the double integration, and it is h by 2 into I0 plus 2 into I1 plus I2 plus I3 plus I4. After simplification, this value is 0.61277. So, this is the value obtained by trapezoidal formula for the given integral. Now, we apply Simpson 1/3 formula to get the value of the double integration, and from the above table we get f I0 equal to integration 0 to 1 f of 0 y dy, which is equal to 0.78539, and similarly for second row we obtain I1 equal to this value, from third row we get this value, from fourth row we obtain this value, and so on. And using the formula derived in equation 89-19, we get I equal to h by 3 into I0 plus 4 into I1 plus I3 in this case, plus 2I2 plus I4, and it becomes this one, and after simplification the value is 0.61684. So, this is the value of the double integration obtained by Simpson 1/3 formula. That means the Simpson 1/3 formula and trapezoidal method can be used to find the double integration, and these methods can be extended to find the values of triple integration and higher order integration. In module 1 of this chapter, that means of chapter 7, we have derived 3 formulas to find the derivative of any differentiable function, and the last 3 modules of this chapter are devoted to numerical quadrature. Several quadrature formula are derived in these 3 modules. Among them, we observed that the Gaussian quadrature formula are better than the other quadrature formula. I would like to mention that the Monte-Carlo method is not suitable to find the integration of a function, but when the function is highly fluctuating, then this method gives more better result than other methods. Also, we have described 2 methods to find the double integration based on Newton-Cotes quadrature formula, but there are several good methods are available based on Gaussian quadrature formula to find the double integration, and all this method can be extended to find the triple integration and higher order multiple integration.